Hey, good morning, everyone. Hi, hello. I know people are going to continue to trickle in, let them trickle. Um, how are y'all feeling about the class? Can I get like a thumb meter of like, this class is easy and I feel secure about my life? And then I'm literally on fire. Where are y'all? Okay. Okay. So some people are like flammable, but no one's, well, I see it on fire. Okay. She's just a girl and she's on. So y'all, lecture three is like when there's a big change, when it goes from like, we're talking about molecules to orgos happening. And I think that like yesterday when y'all were leaving lecture, I saw a lot of faces that seemed kind of shell shocked. And so the purpose of today's section, about half of today's section is going to be just talking about how do we study reactions and how do we break them down and take the information that you learned in lecture and like really learn it. So that's going to be kind of my little TED talk of like how to study reactions. And then we'll go on and talk about some of the reaction kind of families that you learned about. Any general questions or like logistical questions before we jump into things? Cool. I am going to pass around the little attendance sheet again. You can just like write your name. It helps me keep track of like who are my Orga babies. It makes me like try to remember faces and names, all the things. Um, cool. Let's go into the TED Talk. So the first part of it's going to make you feel worse rather than better. And then I'm going to give you some tools for how to approach it. Just heads up. So the part that's going to make you feel worse is in order to figure out how to study these reactions, you need to know very specifically how you're going to be tested. So that's kind of the first big idea. And so I'm going to talk about the ways in which we can ask you questions about reactions. So first of all, when I say a line reaction, do y'all have a clear idea of what that is? I see some no's, I see some yeses. Let's just get everyone on the same page here. So a line reaction is when we say, hey, we have some starting molecule, we have a product molecule, and then we have an arrow that has any other reagents we need or reaction conditions. So we would put like, yeah, whatever accomplishes that goal. And so they can look like this as well. Like here's your starting material, this is your reagents, and then your product would be over here. That is just generally what we mean when we say line reaction, because it all fits on kind of one line. Whereas the other type of information that you have about reactions is a mechanism. That's doing those curved arrows, and that's really explaining how a reaction happens and like why it happens. So now that I've said this, do we feel okay on like what is a line reaction? Hesitant yeses, but cool. So the first type of problem that we can ask you are colloquially called box problems. And it's basically you just plop a box over one part of a line reaction and you suddenly have a question. So instead of just a line reaction that gives you the information like that you would see it in lecture, we would give you a starting material and some intermediates here. And then we would ask like, what is the product rate? So that's the first type of question. We can do like variants on it. So we can do the who done it variant of like, here's where we start, here's where we finish. How did we get there? Like who killed Roger Rabbit? That's what I was going to say. And then the harder way to ask this is we give you a product, we give you some reagents, and we said, what did we start with? Now, this is what most of your questions like this are going to be. You might have one or two like this, and then this is the kind of rarer, harder version. So these are the main two to be thinking about. So box problems, that's like 1/3 of the types of reaction questions that you're going to be asked. You'll have a full page of box problems on the exam, the first exam. For the second exam, you'll have either 2 or 3 pages of box problems. Heads up. Mechanisms. We want the arrows, all the arrows, and nothing but the arrows, so help you God. This is, we give you a line reaction, and we say, using curved arrow formalism, show how this reaction happens. And this is where you are going to do beat by beat, drawing the arrows. We might ask you like even more specifics about like, what are the HOMO and LUMO here? Like what's the donor and acceptor? This is the most detailed type of question that you will be asked. Like in terms of a reaction, this is where you have the most information that you have to give forth. And there are kind of two flavors of a mechanism question. So one I call like a known mechanism. This is where you're basically going to regurgitate the same thing that you did in lecture. So we'll give you like some variant of the reaction that you've seen in lecture, but with just different alkyl groups on the sides. And then you're just like copying the arrows. Like if you had the lecture notes right beside you, you'd be able to get a perfect score on it really easy. The one way that we can make a known mechanism question harder is we could just ask you to do like two of them together. And so that might just be a little bit more difficult because you have to do these two separate reactions and recognize that these are two reactions. The other type is a little scarier. It's a new mechanism. It's like we give you a line reaction for something that does not look similar to what you've seen before. Like it has some weird functional group that you haven't seen, or like it's just not one of the ones that we've asked you to memorize. And so this, we're not going to give you something completely out of left field. It's going to be something that is going to be similar in logic to the reactions you've learned before, but with like one or two little weird kooky steps. And you are going to get a sample of this, like challenge problem 9 this week on this week's problem set is an example of a new mechanism where it's similar to things that you've seen before, but has like one weird step. And the product looks crazy. The product looks like, how are we going to do that? But the arrows are not that bad. Again, this is just kind of exposing you to how you are going to be tested. You should not feel better yet. You should feel worse. Last type of question is the scary one. Synthesis. We'll give you a starting material and a product and say, in 8 to 10 reactions, build the product from the starting material. That's like a big thing. That's a lot. And your answers for these will all be like a series of line reactions where you do a line reaction, draw the intermediate, do a line reaction, draw the intermediate. This is not one that you could do right now. This is like one for exam 2 because you haven't learned some of these reactions. But this is kind of where we are building. And so knowing that you're going to have to think about these reactions as tools to help you kind of creatively build a molecule, that you're going to have to take a step back from these reactions and be like, okay, what's the purpose of this reaction? Why am I using this? And like, when would I want to employ this to build something? So know that we're kind of building up to this like Legos approach. Also on synthesis questions, don't do mechanisms, don't do curved arrows. That's gross, that's nasty. Maybe I don't want any of that on a synthesis question. Synthesis question is just like, give me a like roadmap of how we get there. This is a lot, and this should be a little scary right now. We're not going to ask you to do a 10-step synthesis on the first exam. You're going to build up to it. Joel. So you're going to be responsible for the reagents as well. So like the way that this is graded is you would get like 1 point for this, 1 point for this structure, 1 point for this, 1 point for this structure. So the reagents and the intermediates are important. And then also the sequence of how you order them and put them together. Like there are some reactions where if you do this one first, you won't be able to do this other reaction. And so it's a lot about like planning out consequences. It's kind of like a chessboard or something of like you have all these different players and moves that you can make. But if you lose your bishop, you can't move diagonal. That metaphor kind of breaks down. But like, yes, this is where we are going. So, do you feel like you have a good understanding of how you are going to be tested on these questions and on these reactions generally? Yeah. We will try to give as much partial credit as we can. Some errors are minor and some are catastrophic. And so it depends on like how much chemical logic you are demonstrating and like whether or not that is towards the goal of building the molecule. Because you could just like start with a molecule and do 10 reactions that you know are connected to it, but they in no way are building towards the molecule, and you won't get points for that. But if you are like doing a thing where like you add a carbon or you've forgotten a carbon, then like that's something where like it could be just a -1. Or like it depends on how serious the mistake is. Yeah. There are often more than one. And there are typically syntheses that might be a little bit better or a little bit worse. And if yours works, we will give you credit. We will also typically for synthesis give you a guideline and say the best answer will have 10 or fewer. And so if you do one that has 12, but it works, you're fine. But the best one will have 10 or fewer. Okay, so you know how you're going to be tested on this. Let's use that to inform how we study reactions. So the reaction that was like the scariest from yesterday was the acetal reaction, this big long one. And what we're going to do is we are going to deconstruct this, and you're going to be sick of this mechanism at the end of it. But really, I want to take it as like, this is the information you give in lecture. What are the steps that you should do to study? And so we're going to do it together. And I'm going to show you kind of my process for studying reactions. The big idea for this method of studying that I think is different from how a lot of people want to approach organic chemistry is you have to study the reaction at different levels of detail. A lot of people want to take this mechanism, which is the most detail, and just write it out over and over, and then like hope that it sticks and then regurgitate it on the exam. And like, if you do that, you're not going to be able to do like line reaction problems very well, the box problems. Because if you're having to draw out a full curved arrow mechanism to predict the product on a line reaction, and we give you a page of these box problems that are all line reactions, you're not going to be able to finish it that way. So we need to be thinking about these reactions at different levels and from different angles. So what we're going to do is we're going to start off just by going through the reaction. If you have your lecture notes and would like to annotate on your lecture notes, that would be a good thing. If you are brave enough to zoom in like me and write very small on here on the iPad, then you can annotate on the little section handout. Or if you just want to like write out the mechanism real quick on paper, and then we can annotate it together. We're going to do the process for this hard, scary mechanism, okay? So first thing that I think that you should do before anything is you're starting out at the level of most detail, the full mechanism. And like, this is the most detailed way. And just like what I said, if you only study the mechanism over and over, it's just not going to be very time efficient. And you're not going to be able to answer some of those bigger picture questions. But when you study the mechanism, you should be asking yourself, why is this step happening? And does it make sense why I'm doing these things? And if it doesn't for any of the steps, you need to ask someone. You need to ask a friend. You need to ask a TF. You need to ask Tim. You need to like clear up that kind of like understanding of what's happening so that you can go from like understanding to learning it and grading it. Because if you don't understand it, you're not going to be able to like really entrench it and like use it as a tool. So let's go through this mechanism. So what's happening here? Yeah, we're protonating this carbonyl. And then what's happening here? Just words. Tell me words, what's happening. Well, you're having some attack happen, right? So you're having, what functional group is this? Functional group. Alcohol. Functional group here? Carbonyl, but that's an umbrella term. What's the specific functional group? Aldehyde. So you're having an alcohol attacking an aldehyde. Okay, so why did we do this step? Why did we protonate this? Yeah. You are really close. Yes, yes, that's really great. That's better than the answers I normally expect when I ask why. So let's look at this interaction a little bit more closely. So what's the HOMO and what's the LUMO? What's like the donation that's happening? NO. So we are doing NO is going into what? Pi star CO. Good. So what we are doing here should make this better. So do you remember we talked about the low energy trifecta? And one of the things in the low energy trifecta that lowers the energy of a molecular orbital is charge, right? So we are making this CO, this pi star CO, now a pi star CO where there's a positive charge. And so which is going to be lower in energy? the pi star CO here or the pi star CO here? This one. So the whole purpose of this step is we are making the C double bond O a better electrophile by decreasing the energy of the LUMO. So that's kind of our why of what's happening. Then as we go along, we should also think about kind of like goals for the reaction. I'm going to go a little bit out of order, but like for this reaction, if we look at the line reaction overview of what we're trying to do, what bonds are we trying to make and break? Yeah, so you're trying to, like, one big goal is the break the CO bond. And that's this one over here in the start. And we need to do both the pi CO and the sigma CO. Okay. And then what bonds do we need to make? Well, I guess the first question is this oxygen one of these oxygens? No. And so this oxygen must leave somehow. So we have to break both of these bonds. So that's why we know we need to break the sigma and the pi over here. Yeah. So if this was an O, do you know how to make a bond with this and like an ET? Is that a reaction you've learned? No, so it must not be that. Yeah. Okay, and then what bonds do we need to make? What bonds are kind of replacing that carbonyl? Yeah. Yeah, and specifically two of them. So we need to make two sigma COs with the OET. So these are kind of our reaction goals, and every arrow that we draw is towards accomplishing these goals. So like in this step right here, we made our first OET bond, like we did the one of two of those, and we also broke the pi CO. So we achieved like half of our goals in this one step. This was like accomplishing what we want this reaction to accomplish. Great. Okay. So let's keep going. Next steps. So when this HOAT attacks, we go from oxygen having 2 bonds to an H and an ET to oxygen having 3 bonds, so she's positively charged. We want to get rid of that charge. We make her neutral. Then we're protonating her. And then we have this. So let's look at this step for a minute. Now, there's a special name for this. Does anyone remember the name of like what he called this logic of the arrows here? Lone pair push. Now, Tim kind of buried the lead. This is the climax of the movie. This is the cinematic shot where like Thanos or whatever does the snap and like gets something out of here. This is like a like pushing someone out of the house. Like the way I typically talk about tetrahedral intermediates, it's like 4 friends sharing an apartment, and then one of them has said, "I've had enough of you, get out," and like kicks them out. This is the drama. This is the intrigue. This is the mystery. And so what is the like donor acceptor interaction that's happening here? NO, yeah. And it's turning into what? Sigma star CO. As we all know, when you donate into an antibonding orbital, yes. So this accomplishes our break the sigma CO, our goal here. So with this, we've fully accomplished our kind of green goal up here. So we can almost like think about at this point in the reaction, we've crossed that off, done both things that we need to do. We've broken all the bonds that we have to. Yeah. Yes. He made a little comment of like, it bothers me. But like the convention for Harvard is we just write H plus. Some people are like very like anal about it, and they're like, well, actually, this is a protonated HOET like this, and you know, we really care that you know that it's that. It's not a free floating H plus. Yeah, this is just an abbreviation. But like this is the one where if you write that on an exam, we give full points. Other universities might not. Yeah. Either. Yeah, or solvent, something comes along and grabs it. Like you might also see it written as B with an electrons for like a general base. Just use some abbreviation. What do you remember? Did he use SOL in lecture yesterday? Did he use B or A? Cool. So you can use a general base or a general acid or a general solvent. And I will talk to him about it to make sure. But like the convention for all of Harvard chemistry is you don't necessarily need to know specifically what does the deprotonation, but you need to know something is doing. And so our abbreviation for it is just SOL, something in the solvent. Yeah. It does. It does. It changes depending on what you're in. Like when you're in an acidic solution, you either have things that are acidic or neutral. This would be the neutral version. This would be the acidic version. This solvent would be the HOET. This would be the HOET here, where it has another proton and it's positive charge. Like these are just different species that are in the solution that are less important to know the specific names. Oh, that's where we're going. That's great. So we're doing this cinematic moment where we're accomplishing this goal, breaking the bond. So what did this do to set up this? Yeah. It did. So we lowered the energy of the sigma star CO bond because we made it positively charged. There's another way that we can think about it though. So do you remember what we call molecules that get kicked off? There's a special name for it. Leaving group. So leaving group. And it's often abbreviated LG, leaving group. Leaving groups leave. And so this, my metaphor is when you protonate it here, you're making it so that when you kick it off, it's H2O when it's neutral. Whereas if you just tried to do a lone pair push here, you would have OH minus pushed off. So you're making it more stable on its own, like for when you kick it off. In the metaphor of like the apartment, it's like the roommate you want to kick out, you're packing their bags for them. So you're making it so that it's easier when you forcibly evict them to just like go and look for a new apartment rather than to just be angry and reactive. Yes. Yes. Just because this is a little bit beyond where you are right now, there are ways that you can measure how good of a leaving group something is and also how strong of a lone pair pusher something is. And if you didn't pack the bags here, if you didn't protonate this, you wouldn't be able to do this lone pair push and kick it off. So, yes. So we are lowering the energy and making a better leaving group. And then this, we can also reconceptualize this as not just neutralizing it, but making sure that this has the lone pairs to do the lone pair push. So set up OET for lone pair push. Okay, yeah. Yeah. That's a good question, and it's complicated. It's hard to give you a solid answer. The thing I like about SAW is you don't have to specify, where you can just say generally something happens, and like it depends on how you prepare the alcohol. Is it a 100% alcohol solution and you dropped in HCl and made it acidic, or did you like add H3O plus to it and so there's water in the mix? Like it becomes a more complicated, nuanced thing. Whereas if you just use salt, you don't have to answer that question. I'm gonna go keep plowing and then we'll address more questions as they come. So now we're at this setup, and this looks eerily familiar. What does this look eerily familiar to? Boom. So our donor and acceptor the same? Yeah, lone pair in auction attacks the pi star CO. And in doing this, we make our second OET bond. So we do 2 of 2. So we can go up to our goals and check that off. We've accomplished all the goals that we want to do for our reaction. Oop. So at the end of the day here, last thing that we have to do is just deprotonate it to get our neutral product. You look very confused. Do you have a question? Yeah. Oh, wow. My handwriting. That's what was causing the confusion. Yes. So this is the like first ripping off the Band-Aid, understanding why each step is happening. This is the baseline. Let's try the step 2. So the step 2 is we're going to go through the mechanism again. And now what our goal is going to be is we are going to try to summarize each step into a few words in the English language or like some symbols. That just gives us a shortcut and it translates the visual information of reactions into words. And y'all are much better at memorizing and learning words. Like that's what you've done in many other classes. So like what would you describe this first sub-step? Yeah, I would say protonate the C double bond O. And if I just said this and did not give you arrows, is this an arrow that you know what it looks like? Yeah, like this is just the acid base arrow. And like, this is the whole key. When you are writing these shortcuts, write as much for this description as you would need to write the full arrows. So it should start off maybe a little bit more verbose. And then as you get more confident with what these arrows look like and the patterns, you do fewer and fewer words. So what about this second step? Well, I would probably just call this alcohol nucleophile attacks carbonyl electrophile. And this is just like a statement of what happened. It's not the whole why and understanding what happened, but like I know that when I attack the carbonyl, I'm going to have to do a second arrow because this carbon already has 4 bonds. And so I don't need to make an extra note of that. And this is the most concise way I could say this. Now, the next 2 steps I'm going to group together. What is this? Like, what would you call this? Louder. Deprotonation. We're just taking off a proton. What would you call this step? A protonation, right? So when you have a deprotonation and a protonation right back to back, we give it a special name that helps us just kind of think about the overall what we are doing. We call it a proton transfer, which is often abbreviated PT. So the proton transfer to make OH a better leaving group. Now, proton transfer, what it looks like is if you just compared the start of the proton transfer right here with the product, it looks like, oh, this hydrogen just transferred over here. It just popped over. In reality, it's not the same proton. It's not the same hydrogen moving over, but it's helpful to think, oh, okay, I need to remove one from here and add it to here. It's like we're transferring where that proton is. Okay, and then we already called this 4th step what it is. A lone pair pushed off H2O. Okay. Then what is this 5th step over here? This one, the deprotonation? Oh, the last one, yeah. It's exactly what's up here. Alcohol nucleophile attacks carbonyl electron. I'm just going to copy and paste her. And then you're totally right that this is just a deprotonation. So at the end of the day, what we can do is we can get this little list that says, hey, in our 6 steps, this is what the whole visual, all the arrows and structures we're doing. And like, if I gave myself a line reaction and then this, I could get the full mechanism. Like this is enough instructions for me to write the mechanism. And it's a way of like studying mechanisms where you're not actually doing arrows and structures, which take a lot of time. There's one step further to this part of like the labeling it. And it's kind of like taking a step back and be like, what types of arrows are we doing? What is the logic behind this mechanistic step? And so one type of logic is acid base, like protonations, deprotonation, proton transfers. So how many steps here are just acid base? I get fingers. How many steps here? 1, 2, or 3 are acid base? There are 3. We have a protonation, a deprotonation, and our proton transfer is just acid base. And acid base are arrows that we taught you in the first lecture. So like acid base arrows are only going to get easier as we go along. And so recognizing, oh, okay, I'm doing the easy arrows that I learned at the beginning, and I'm just doing it 3 times in these kind of different circumstances. It's helpful for me for organizing. The second type of logic that you've learned is a nucleophile attacking a carbonyl electrophile. And that's really the whole theme of the like lecture 3 reactions. Like all the ones that we taught in lecture 3 are grouped together because it has some nucleophile attacking a carbonyl electrophile. So that happens twice here. And the only different type of logic that happens after that is a lone pair push. That's its own kind of step that's a little bit different with the arrows of making a carbonyl, kicking something off. And so being able to identify, hey, these are my 3 chess pieces, and I'm just doing this kind of weird dance where I'm doing them in this order, but I'm really just doing these 3 moves over and over again. To me, this is like a much deeper way of thinking about the reaction than like, oh yeah, the second thing I need to do is like protonate. Like it makes it a kind of more complex like understanding of what's happening. And it also is developing these kind of patterns and schemas that you can mentally go back to and like reference. And like this is setting you up for thinking about future reactions. Of like in future reactions, are you going to use these mechanistic logic? Or are you going to be learning a new type of mechanistic logic? Yes. These 3 can dissect the steps of all the reactions you did yesterday. Yes. And then as you go on the course, you'll get a few more tools, but you really are not going to learn more than like 7 different types of mechanistic logic. And then it's just about the scenarios that we use them in.
I think the other thing for studying is like what subject to take. In this reaction, is it always going to be everything is identical, or what can change and it's still that type of reaction?
So it's going to be anytime we can do it with any alcohol. So it doesn't matter what it could be ethanol, it could be methanol, it could be isopropanol, it could be any alcohol. And the other thing is this could be a ketone or an aldehyde. And then you're always going to be making the acetal. So do you remember like in section 2, I think, I had a thing with functional groups that was talking about like why we use functional groups. It's so that these are not all separate reactions. It's just one reaction and we're changing what these R groups are, like the different kind of side components. That is what we are doing here. Like this is one specific reaction that we are saying, hey, from these functional groups, generalize it, write out the version that's just R's here. So like we could just put an R here, and R just stands for any kind of alkyl group. And then that could be an H or an R. And then this is an ROH, And maybe let's call it R prime because we have two R's, and if we have two R's, it's a little confusing. Then we're gonna get an R, RH, OR prime, OR prime. This is kind of like the generalizing version of it, which I know I did kind of quickly, but does that make sense so far?
And that should change our arrow. It will change like what's on it, but the arrow should stay the same.
Exactly. And the logic, the things that you wrote out right here is going to be the exact same.
Thank you.
Yeah. So that's kind of like the key thing for me for studying mechanisms. It's also going to help you with those new mechanism questions. We're going to have to do something a little bit weird. If you really know what types of arrows you can do, then you know what is new or a little bit weird as well. So let's switch gears a little bit. And we've done a lot about studying for the mechanism, but how about studying for those box problems, the like line reaction questions? I would encourage you to think of studying line reactions as like a distinct but kind of connected skill. So if you are doing the whole predicting what the product is by doing a full mechanism, it's just not going to work on exams. And so the solution to that problem is make a fake mechanism. So fake mechanisms will say things like erase this bond or put this over here. Like it is truly like an instruction on how to physically write what the answer is. It is not something about how you understand the reaction. So let's try to make a fake mechanism for here. Like if you had to give yourself instructions on like just how to write this product, if you were only given this, what would you say? How do you write this product if you were just given these starting materials? Yeah, so erase, double bond to O. And then what are we doing? Yeah, we're attaching to O, and then this is whatever is the R group on our alcohol. So replace with two ORs. So let's try out that fake mechanism on another one of these acetal questions. So here is my ketone, here's my alcohol and acid. What I'm going to do is I'm going to erase the carbonyl. So I'm just going to draw the base right here. And I'm going to add two ORs. What is our R group here? For our alcohol, what's our R group? Which is called propyl. Yes. The 3-carbon one is propyl, methyl, ethyl, propyl, butyl. So we're going to do one O and then 1, 2, 3 carbons, and another O, 1, 2, 3 carbons. If you wanted to even break down the fake mechanism further and do like replace with two, like just this much, and then step 3, add the R group onto the O, that's also a valid fake mechanism. Just whatever tools you need to write the correct product from the starting materials. And you're not going to be able to do this with a reaction you've never seen. This is only something that we give you the mechanism in class, and you can build a fake mechanism that you can reproduce in other circumstances. Yeah. It's based on the reaction. So like basically it's not a thing of how to figure out what will happen. It's a thing of we told you what's happening. How can you like write the correct thing of the product? And so this reaction, you're always going to add 2. The hemiacetal reaction, you only add 1, but that's typically done in base. And so like when you start the hemiacetal reaction, you do that separately and you do that process of erasing and your fake mechanism is going to be different. The acetal reaction. We are just doing the acetal reaction right now. Yeah. But this is the process that I would recommend doing with each of those reactions to break it down and make sure you understand what's going on and looking at it from these different angles. I'm going to keep going real quick and then I'll do some more. So the last little bit is, or just one quick warning, don't only learn the fake mechanism. You still have to know the real mechanism for mechanism questions. but this is just a helpful tool that you can use. The last kind of level is zooming out further and further, and it's kind of big brain, and it's for those synthesis questions of thinking about, why are we asking you to learn this reaction? What is this reaction a tool to help you do, and like what types of molecules can we make? And so for that, I kind of identify goals and purpose. So goals we've already done. Play a spot the difference game and figure out what bonds need to be made and broken. And that can be a guideline for what your arrows are trying to accomplish. So that part we've already done. The purpose is the deeper question, like why do we do this reaction? And the typical purpose for most reactions is going to be to interconvert or to convert between functional groups. So if we look at this reaction, what do you think the purpose is? Specifically what? Yeah, that's it. Like literally, I know it sounds like a dumb purpose. It's to specifically reversibly. That's one of the things that's significant here. Interconvert between a ketone or aldehyde plus an alcohol and an acetal. And there's kind of a deeper purpose that you wouldn't be able to see just by looking at the reaction, but that we are telling you. And do you remember Tim using the phrase protecting group? Yeah, he threw it on at the very end. You're going to see it more in the homework and everything. So this is also an example of what we call a protecting group for a ketone or aldehyde. The basic premise is like, let's say we have a molecule and we have a ketone and we have another part over here that we want to react with, but we don't want to react with the ketone. What we can do is we could convert that ketone into an acetal. And acetals are not super reactive. And so your other part that you're trying to react with, we can do whatever reaction we want to do with it because our ketone's protected as an acetal. And then we can go to our product where we have our ketone intact. We can remove that protecting group. We can put on the acetal and then take it off. And then we have our like new thing over here that we've added. That's the general idea behind the protecting group. This kind of like deep layers of thinking about it is what I would encourage you to do for studying reactions. And this is the method that once I started doing things like this, I was not doing this right out the bat, but there was a specific moment for me in OChem 2 when I realized, oh, this whole class, I'm just going to be learning new reactions. And I need to figure out how to take them in and digest them, essentially. Like, so not lecture 4. Lecture 4 is kind of weird. Lecture 5 through 10, we're going to be giving you 7 to 14 new reactions each lecture. And you're needing to build up these as kind of arsenals of tools or weapons or whatever to do chemical things. The metaphor that I use is like a toolbox. And this whole purpose question gets you to think about reactions in terms of like the little compartments on the toolbox. Like reactions that have a similar purpose are all in the same kind of like wrench section of your toolbox, whereas reactions that accomplish this other purpose are in the screwdriver section. Like this is what your toolbox of reactions will look like if you don't think about this higher order, how to organize them, fit them together. And I have done something for y'all. If you go to the last page, I've made a review sheet that does this process of all the reactions in lecture 3. So it goes through each of them, it organizes them into different families. And for each family, it has the general purpose for each of these. And typically things in the same family have very similar purposes. So like here, this acetal reaction is in the reversible carbonyl additions family of reactions. And the purpose of the family generally is to reversibly interconvert between a ketone or aldehyde and some other function. And so all of these are fairly similar because they are doing that purpose. I will also say all the other reactions that you learned are like 2 steps, whereas the one that we just did today is 6 steps. So not all of them are going to take this full half hour to go through and study and digest them. But like, I really want this whole like thing that we've just done to be like a set of tools that you have for taking on new reactions. this is also a trap, like I wrote that fairly big. If you just use this review sheet I made and do not go through the process for yourself of like going through each reaction, trying to make your own kind of like sheet that organizes it and compartmentalizes all the information, you're not going to learn it well. Like this is a trap. But other questions on this whole process of how to study reactions? Yep.
Just given them acetyl compounds and we're asked to go in reverse direction, they can tell us.
It depends. So if it's a mechanism question, we will typically give you what the product is going to be, and like you'll be able to see it. But if it's a line reaction, like I mean, you should do this and be like, what is the fake mechanism for going the opposite way of starting an acetal going to a ketone aldehyde? And then because this is a reaction we've taught you, you should be able to predict the products just in a like line reaction form. So it's something that you have to learn, like in study specifically. Other things about like how to study reactions. Yes, but again, it's like memorizing and understanding, and memorizing not just by like writing out reactions over and over, not just by doing like flashcards of reagents, but by doing some kind of combination of things. Like study for synthesis questions, study for mechanisms, study for line reactions. And as long as you're doing something to study for each of those, you should be in good shape. But like if you just do one method, if you just do flashcards, it's going to be inadequate, which is frustrating. Like this is like very rich information that we're asking you to learn, and not just learn it, but to be able to apply it. Like it's a very kind of like you have to understand it to be able to apply it and use it and do those like big synthesis questions where you're having to piece everything together. Do y'all feel any better, or is this just stressful? I see a couple light nods and a thumbs up. Again, it's hard, and I don't want to like BS it with y'all. I don't want to be like, oh yeah, oh, you're struggling? That's weird. Like, no, this is a lot. But thank you for coming to my TED Talk. I will get off my kind of like high horse of this is how to study, like, and we will go to our normal section. Cool. Okay, so let's talk about the first family of the carbanion equivalent reactions. So the purpose of these whole family of reactions is we are trying to add an alkyl group to a carbonyl compound of a ketone or an aldehyde. So the thing is, carbon, we would want a carbon nucleophile like this, like a CH3 minus. But do you remember what the issue with this compound is? Super high pKa. So like, basically, you're never going to be able to make just a CH3 minus. So to get around that, we do these kind of weird bonds between carbons and metals. So compare it to a carbon-oxygen bond. In a carbon-oxygen bond, which side is more partial negative? Oxygen, partial negative, and carbon's partial positive. When you're bonded with a metal, most metals have an electronegativity of less than 2. So carbon is 2.55, and this is less than 2. And so we're going to have actually the partial negative on carbon this time. Interesting, very interesting. And actually, typically the difference is so big, it's almost like it's an ionic bond. It's almost like we have a carbon with a negative charge, which is what we're trying to make, like our equivalent of like a carbanion to go and attack something. But for the purposes of our class, we're going to want you to draw it as this sigma bond is what goes and attacks. Now, when this sigma bond goes and attacks some electrophile, which thing is making the bond to the electrophile? The carbon or the metal? Carbon. Because think about it as like carbon's in a marriage right now to the metal, and carbon says, I want to get married again. I want to have a different marriage. And so it takes its electrons from the marriage and goes and marries the electrophile, and you have carbon electrophile like this. And then you just have the metal that kind of pops off. It just falls off. You don't really need to write it. You don't really care about it anymore because it's just this inorganic thing. And so it's just kind of in the mix of. Cool. So that's kind of overview of it. let's meet the first two main players, our first two reactions. So we have the Grignard reaction and the alkylithium reaction, which are both accomplishing the same goal of we start off with a carbonyl and then we add an R group. Now, because we are adding an R group to a carbonyl, we happen to make an alcohol. So we typically don't do these reactions because we want to make an alcohol, but it's more so that it's hard to make carbon-carbon bonds, and this is a way to do it. So a couple of like features of this. So H plus workup, this is kind of general. Like this is like using Sol of like, there are many acid workups that you could do. Some people like some classes you write acid workup, some you write H3O plus, some you write HCl, some you write H2SO4. We don't care that you know which acid you should add to quench it. We just care that you know that there's going to be an acid added, and that's the second part of the reaction. And so we write it as an H plus workup. Also ET2O, who is she? Her structure looks like this. So it's diethyl, you have two ethyls on an ether, an oxygen with two carbon things. And so our little oxygen back. And I know Tim said that Grignard is like French. I did not know that. I always thought Grignard was like the name of a vampire or something. I was like, oh, the vampire needs his little oxygen bats. And so that's how I thought about it. Now, these two are on the same line, but this ET2O is just the solvent. It's just the kind of like medium where the reaction's happening, but it doesn't participate in the reaction. So you'll never draw ET2O doing something in a reaction. It's just kind of like the solvent of what is in the beaker, the like medium that the reaction is going to take place in. Also, note that there's a specific step 1 and step 2. So this means you start off with this and you add these things to a pot and it's in the beaker and it reacts completely. Once that is done completely reacting, then you add in the H plus to the beaker. So they are completely separate steps. If you did not put the 1 and 2, then it was going to be wrong because this says, hey, add both of these into the beaker at the same time. So this R and GBr, RLI for whatever R group you want to add, how do we make those? That's kind of the first question of where we start. So we start off in an alkyl halide. Like let's say we wanted to add an isopropyl group like this as our R group that we want to add over here. Well, we want to first make this isopropyl MgBr. Okay, the way that we do that is we have to start off with this isopropyl bromine, and then we add magnesium and diethyl ether, and that's what makes our Grignard reagent. Now, this reaction right here, you do not need to know a mechanism. You also don't need to know a mechanism for the one that makes the alkyl lithium here. These are just going to be line reactions. These are just going to be like box problem tools and synthesis tools. So if you want to make the alkyl lithium version, you just add lithium and diethyl ether. Right now, this is all just kind of memorization, which is rough. The mechanism for both of these are the same though. So you're going to have the carbon bond to the metal, which is either the Mg or the Li. And the sigma bond goes and attacks the carbonyl, push up. Then you're at your tetrahedral meteorite. All you do is protonate it, and you're done. Such a nice reaction after the acetal reaction. Questions on the lithium or the Grignard? Yep. We'll get to that. The Grignard specifically is MgBr.
The person question. Really not, I believe.
Yeah, like let's say a simple synthesis would be like if you started off with a carbonyl here and somehow in the product you need to have in that spot an OH and you've added an ethyl, then you know that you're going to need to use some sort of either Grignard or alkyl lithium to add this ethyl. Yeah, Joel. Oh, it doesn't matter. It's tetrahedral. Yeah. So like if you drew the R here and you have the methyl here, that's totally fine. So this is kind of the base family, and then you're going to get to know the quirks of the family. So the weird uncle of this kind of family is reacting with esters. So first we react with ketones aldehydes. With esters, instead of adding just one R group, we're going to add it twice. So start off with an ester, you add 2 of your R group, whatever it is. And the reason is because of this step right here. So the first step here is exactly like what we saw before. But how is this step different from the one that was in the attacking just a ketone? Oh, I heard someone say there's a leaving group. Well, oh, I did put that right there, didn't I? Yes, that's exactly it. So here you have the option of doing that lone pair push, reforming carbonyl, kicking off a leaving group, OET minus. Over here, if we tried to reform a carbonyl, the only thing that we could kick off is like a carbon thing. And do you think like CH3 minus is a good leaving group? No, she doesn't like that negative charge. Whereas OET is fine with the negative charge. It's an oxygen, it's more electronegative. So when we do that, we reform a carbonyl. And so we can do the exact same arrows that we did over here and just have it attack one more time and then do your little acid workup of just adding the hydrogen. So whenever you see esters, especially for exam 1, the only reaction that you will know that esters do is a double addition. And so you should be like walking between classes and be like, ester, double addition to esters. You should be like sitting down in your chair, esters, double addition to esters. It's like one of those like mantras that you will repeat to yourself. So like literally on the practice exams, if you see an ester, you should be thinking, thank you. Well, because esters have this is the leaving group, this OR that's on here. So esters always have a leaving group built in. Now, we have a kind of tricky thing when we have, I'll get in one sec, when we have an enone. So do you remember I talked about those compound functional groups where it's like there's resonance between these? And so instead of being an alkene and a ketone, this is one distinct thing. So she's kind of funky because instead of just having one spot where it can be an electrophile, there's another option for where we can attack it. And so basically there's this arbitrary numbering that some chemists did in the 20s or something. And if we attack at the normal spot, we call it 1,2 addition. And if we attack at the end of the double bond to carbon, we call it 1,4 addition. Now 1,4 addition is also called conjugate. So this hard soft you can ignore. This is kind of like an FYI for MCAT thing, but Tim did not use this language. Like things, nucleophiles that add 1,4 are called soft nucleophiles. Nucleophiles that add 1,2 are hard nucleophiles, but we don't need you to know those. But let's get into like why this matters. So if we did our Grignard, so we have R and GBR for whatever R group we're trying to add, our solvents, diethyl ether, then we have an H+ workup. We have an issue because Grignard is going to react with whatever. It's going to react and get a 1,2 product and a 1,4 product. And so if we're trying to make a specific molecule, Grignards don't help us if we're trying to react with an enone here. And so we need versions of this reaction that will only add 1,2 or only add 1,4. Does that make sense of like, this is the scenario of why we have multiple reactions that are accomplishing kind of the same goal? So the one that only adds 1,2 is our alkyl lithium. So we do our RLI, ET2O with an H+ workup. Now, we also need a version where we can add just 1,4 because sometimes we will want to add things at the 4 position. And so what we do is we take our lithium and we sprinkle in this copper halogen compound. So I'm writing a CuX. So in a specific version of that could be like CuBr or CuCl, something like that. And then you still have your diethyl ether. And I wrote a 2 at first, sorry, it should be a 1. And then 2, your acid workup. Now, when you sprinkle in the copper, it makes this interesting compound here called the Gilman reagent. So it looks like a copper is associated with two of those R groups, and then the lithium is kind of like an ionic bond here. So if you, instead of writing two things here, wanted to just write one thing, you could replace this whole thing with R2CuLi. So let me give you a specific example. Let's say you wanted to go from this to adding a methyl down here, a CH3. What I would do is I would do methyl 2 CuLi with your Et2O, and then second an H plus workup. So that's going to be the one that adds only 1,4. The other way you could write it is methyl lithium CuBr Et2O. Does that kind of make sense? Go ahead. Yes, it's just the form of like how she like comes. Yeah. Yep. So this is the thing. The why of this is kind of harder to answer. Like I don't have a good answer for why the Grignard reacts with both, other than it's very reactive. I also don't have a good answer for why the lithium only adds 1,2. But like people were like messing around in lab trying to do their chemistry PhD 80 years ago, and they discovered, hey, this is what happens. And so if you're trying to do this one tool, you use this version. And so it's more so like the understanding the why of the 1, 2, 1, 4 here is not going to be what we ask you. We are going to ask you to employ the right one to accomplish whatever goal you're trying to accomplish. But that's a good question. Because the Grignard, I think, is going to be kind of a solid, and then carbonyls are going to be kind of like oily. And so if you just put like the solid on top of the oil, I guess it would react right there at like the front of it. But if you kind of put it in diethyl ether as a solvent and kind of dissolve them and mix it up with the stir bar, then it's going to react more fully. Like that's why we have the diethyl ether as a solvent. Yeah. So one thing that I want to explicitly say is the mechanism here. So this mechanism for a conjugate addition, adding 1,4, is different than the normal one. And it's just like slightly weird because you have some resonance things happening. So one flavor of 1,4 addition is a thiolate addition. And this is one that he did as kind of like a side note at the bottom of the page. So what is a thiolate? Where have you seen thio before? Yes, an SH functional group. So a thiolate is like RS minus. So it's S with some sort of alkyl group. And the thing about thiolates is they add 1,4. So this is the other one in this family of conjugate addition that was just kind of rando that he threw in there. And that's why I was like, I'm going to bring it up here on the section notes. So you're going to have your S minus, and it's going to be the nucleophile, and we're going to add 1,4. So our first arrow, we go and attack at this bottom carbon. And then what bond do we break? The pi bond, yeah. And so we're going to move those electrons up here. But then we have an issue because this carbon already has 4 bonds, right? So we're going to push the electrons all the way up to the carbon. And this is the whole like first step that's a little bit weak. Whereas if we had just attacked the carbonyl, we don't have to do all these arrows. It would just be those two. So when we do this, what we form, this is kind of the single bond structure of what we formed. And then we kind of trace what the arrows did. So this moved up, and so we have a negative charge up here. This arrow made a double bond at that position. So we have a double bond here. And then this arrow created a bond between this carbon and the sulfur. Work. So that's our structure. Okay, so to get from here to here, it's clear that we need to make a carbonyl, but what else needs to happen? There's something kind of subtle that's between this carbon and this carbon. How are those different? Sure. Hydrogen. So on this one, there's only one hydrogen, right? And over here, there are two hydrogens. So essentially, we need to add a hydrogen at that point. So what we do is we're going to push down, form our carbonyl, and then these electrons are going to go and grab a hydrogen from something in the solution. And we can just write that as HB for some general base, or actually in this case, we might do HA for some general acid. Because some acid's going to be giving up that hydrogen, and this is just an acid-base reaction, right? Like this part right here is just an acid-base, where this acts as a base, this acts as an acid. The exact identity you don't need to know. You can just use a general something. You could even do like H sol. Something like that shows that you know what's happening, even if you don't know what the specific molecule is. And then that takes us to our product. Yeah. Because we need to reform the carbonyl.
Oh, that's.
Well, it's kind of like, again, this is a compound thing. Like these are connected via resonance. Like you could do a resonance structure where it's like this. So all of these atoms are linked. So if you're making a carbonyl here, you need to do something with these electrons. And what you're going to do is have them go and grab a proton. Yeah. It's the solvent. And so it could be the thing that's over here that you grab the H from. But again, the specific identity doesn't matter as much. Again, I'm going to double check with Tim because this is what we've always done in the past. And this is also what 17 and 27 do. But I want to make sure that that's the convention he's going to do. Cool. So with like 5 minutes, try out some of these. And I would actually encourage you to start off trying out some of these box problems, which I think is page 9. And then there's one mechanism for you to try out. And I will be kind of circulating and answer some questions. Alpha groups right here. 7-Eleven, magic number. Let's talk about some of these box problems. So for this one, we had an ester. The first thing that you should think is double addition to ester. So what is the thing that was added twice over here? Methyl. We have two methyls that were added. So for esters, we can use either the lithium or the Grignard. So which do you want to use? Grignard, sure. You're going to do methyl, MgBr, with our diethyl ether, and an acid workup. Done. Yeah. Both of them are equal. The only time that the difference matters is if we're working with an enone. Speaking of enones, oh my gosh. So this one I couldn't find actually in your skill builders when I was looking at your problem set. So maybe this is one that we like retired and took out of circulation or something. So I will check her. But here we are adding two alkyl groups. What are the two alkyl groups we're adding? Ethyl and a phenyl. Yeah, and remember phenyl, that's like a benzene ring over here that we're adding. So we need to add something 1,2 and something 1,4. Now, which do we want to add first? 1,4. So when you add 1,4, the product of the 1,4 addition has a carbonyl. And so then you can do a 1,2 addition afterwards. But if you add 1,2 first, then you no longer have a carbonyl and you no longer have an enone. You just have an alkene. And alkenes, you don't know any reactions with her yet. And so we're always going to do our 1,4 first if we're having to do both of them. So we're adding our phenyl group 1,4, a pH 1,4, and an ET 1,2. And so what reagent do we use for the 1,4 addition? Grignard, lithium, or copper? For 1,4, copper. 1,4 is copper. So I'm going to write pH2 CuLi because this is the R group we're adding, the phenyl group. And then our solvent Et2O. The or you could write it as PHLi CuBr Et2O. And then we do an acid workup. And then just as a kind of benchmark, we can see, okay, then the thing that we are reacting with is this. And so now we have just a ketone and we're trying to add this ethyl group. So what should we use? Grignard, lithium, or copper? Lithium or even Grignard at this point. Like at this point, there's no options for like add 1,2 or 1,4. So use whichever you want. So let's do the lithium just cuz. So we do ETLI, ET2O, and an acid workup. Last one, which is a little bit weird, which is why I want to talk about it, is here, we don't have a carbonyl, do we? We have a ether. We don't know any reactions with ethers. And we have, I guess it's an alkyl halide. Do we know any reactions to alkyl halides? You're nodding. The only thing we know how to do with alkyl halides is turn it into a Grignard or turn it into an alkyl lithium. So let's turn it into a Grignard. So if we add Mg, full 0, and Et2O, then what we've made is this whole little ring, and then it's an MgBr. So this is a nucleophile that can attack some carbonyl. But still, we don't have the carbonyl. But let's trace like where this is in the product. It's here, right? And so if this is a bond right here that's going to go and attack something, it's going to attack this carbon. So let's turn that carbon into a carbonyl and see what it looks like. So if we kind of do our thinking backwards, we have here with our OMe, and we have our MgBr, and then we have a carbonyl, and then what else is on this carbon? What's on the carbon right here? What is this carbon attached to? Two hydrogens. And those hydrogens do not come from a reaction, they're just on there. And so this is the carbonyl that our Grignard needs to attack. And so this is kind of the weird thing. So step 2, what we add is our carbonyl with those two H's on the sides and a diethyl ether solvent. And we are doing our Grignard, but it's kind of weird because our Grignard reagent is over here. Like we are starting off with this and then we are adding the carbonyl. But that's the same thing as if we started off with carbonyl and added the Grignard. And then we just do an acid workup to quench it. Go ahead. So do you agree that like if we add this, we make the Grignard? And you agree that this carbon is what's going to do the attack, right? Because that's the carbon in GBR bond. And so I look for this. And so this must have attacked something here, this carbon that I put a dot on. And that's this bond is what the result of the Grignard reaction is. But I know that the Grignard only attacks carbonyls. So instead of having an alcohol, I know it's this carbon with a double bond to an oxygen. And then it's about figuring out what else is attached to it. Well, the other two things that were on here were hydrogens. This is a hard question. And this is one that I don't think any of you I would expect to do right now, which is why I wanted to talk about it. Yeah. This attacking here converts it to the alcohol because it breaks the pi bond. And then it's technically an O minus, and then the acid workup, you go grab the proton. Yeah. Step 3, the acid workup. So if you did 1, 2 first, you would get this. Right? So from here, where is a carbonate?
Oh, Rex is one.
These reactions only add to carbonates. Yeah, exactly. Exactly. And so like here, you're just left with an alkene and you don't know any alkene reactions. These don't add to alkenes. They add to enones or ketones or aldehydes or esters. Okay, I know it's a lot. I know it's hard. Let's talk about hydrides real quick. And I'll do more questions at the end, okay? So the second family is the hydride reactions where we are trying to reduce a carbonyl down to an alcohol. So this is, we want to get to the alcohol, but we don't want the baggage of adding a carbon thing. We just want to add a hydrogen. And specifically, we're adding a hydrogen with its electrons, which is called a hydride. Now, a hydride, we could just use NaH, but NaH, it's something that's a strong base. And so you're going to use it for like acid base things later, but it's a really poor nucleophile. It doesn't want to just attack on itself. So we want something that's more reactive than this NaH. And then for H+, like a lot of people want to be like, okay, just have H+ attack. Does H+ have any electrons? Can it act as a nucleophile? No. And so you need a way of getting the H with its electrons, just like we needed a way to get carbon with its electrons. And so we use hydride equivalents. So we use AlH4- and BH4-. And with these, the formal charge looks like this. So we draw out the Lewis structure, and we would normally put a formal charge of the negative on the boron. But if we look at electronegativities, that's not what's happening. So electronegativity is hydrogen is 2.2, boron's 2.04. So it's actually going to be a partial negative on the hydrogen and a partial positive on the boron. This formal charge thing, it's kind of just like our accounting tool of there is a negative sum, but it doesn't necessarily tell you where the electrons are, especially with boron and aluminum. Those are kind of weird elements. bonds. And so I just want to note that that's a little bit weird. And so you can treat this hydrogen boron or hydrogen aluminum bond just like an H minus, essentially. And so this bond can act as a nucleophile, attacking electrophile, where you create an H electrophile bond, and then the BH3 just falls off. Same kind of idea. So for this, we have two flavors as well. We have the lithium flavor and the boron flavor. They both have the same mechanism generally here, where you have the sigma bond go and attack the carbonyl, and then you need to neutralize it. And for the lithium aluminum hydride, you neutralize it with a separate acid workup step. And for sodium borohydride, you could just do this as H-sol, where our solvent is methanol, MEOH. So if you want to do HOME and do it that way, you can, or you can do the general version. Now, why do you have the two versions? Like, why do we give you two reactions for this? Well, they have kind of different characters to them. So lithium aluminum hydride, she is very, very reactive. She will like dominate a kind of reaction vessel. She reacts with ketones, aldehydes, esters, and she reacts with even more things that you haven't that you will learn later. Whereas sodium borohydride, soft boil, only reacts with ketones or aldehydes, very mild, gentle. So also because of this reactivity difference, lithium aluminum hydride, it needs to have two steps. It needs to have first step where it does its reaction, second step with an acid. Whereas sodium borohydrides can get along with people. It's a bit more mild. And so you can put the solvent, the thing that has the H, and sodium borohydride together, and they won't react. So lithium aluminum hydride, toxic, masculinity, kind of like aggression, and softly. Now, we also have the enone question for hydrides, but it's a little bit easier because you're just going to get 1, 2 no matter what. So lithium aluminum hydride or sodium borohydride, add 1, 2 or 1, 4. But if you're doing sodium borohydride, you have an Uno reverse card. And that is if you put CeCl3 in, then you only get the 1, 2 product. The why of it does not matter. The mechanism you do not need to know, other than it's just adding 1, 2. The CeCl3 just controls for it being 1, 2. Whereas if you didn't have that, you get both. Work. Questions about her, the differences between these. All right. Why don't you try doing? Why don't you try doing this problem right here? Just take a minute or so. You finish that if you want to look at this question. Bottom one, we have an enone, right? And did we add 1, 2 or 1, 4? 1, 2, because we still have this carbonyl, and or sorry, this alkene, and this alkene would have gone away if we added 1, 4. And then at the 1, 2 position, we have this hydrogen. So we just said, what's our Uno reverse card? Yes. And also her government name is the Loosh reaction, which I think is fancy. So just be like, oh, I just did a Loosh reaction, it's fine. So we do our NaBH4 with our methanol solvent, and then add in the CeCl3, and then we don't need a second step. So oftentimes for these box problems, you don't have to use all the steps. It is saying in 2 or fewer steps, do this reaction. So this is just a one-step reaction.
Or you can just say like, I'm solving a big, big.
Yes, because this is mild. So like here, when you have the sodium borhydride, that's like your this right here, NaBH4, and then you have HOMe in the same solution. And that's okay because this thing is not going to react with this because it's mild. But if we have aluminum or lithium aluminum hydride work, this, if you had H plus around, or if you had methanol, it's going to just deprotonate those and not react with the thing we want it to react, not react with our reagent. Yeah. Yes, because it normally, like, I mean, in the lab, it would be slower, like you would have added it, nothing happens, and then you add the second thing. Specifically, if you put CCl3 second, then yeah, it wouldn't work. You would, because it's like you put a solid and an oil together and then sprinkled in this metal thing. The reaction's gonna be really slow if you don't have a solvent to dissolve it all and put it all. Yes, and then when you add in the solvent and mix it all around, your reaction would happen. But it shows that it's like a misunderstanding of like what we are doing and what each things are being used for. So sorry, I did this last time as well. I want to wrap up like 2 more things and then I'll take some questions generally. Now, what about this? So what functional groups do we have in our starting materials? We have an ester, and what type of carbonyl do we have here? Ketone, okay. And our products, what functional groups do we have? We have an ester and an alcohol, good. So we want something that's not going to react with the ester because she's just going to stay the same. And then we want something that's going to add a hydrogen over here to where our ketone was. So which should we use? NaBH4, because that's the soft boy. Soft boy will not react with esters. So I know both of these were like a question of like sodium borhydride. What if we wanted to get to the product that looks like this? Lithium aluminum hydride and the acid workup, because we want to react with both the ester and the carbon. So the last family of reactions that we are not talking about today, and I did this intentionally because we already did the acetal to death, is those reversible carbonyl additions. And for those, I think it's going to be helpful for y'all to group them in terms of the acid catalyzed ones and the base catalyzed ones. The acid and the base ones, other than the acetal, follow the same general steps here. And so as you go through and like work through each of those, you can like check that they all kind of fall into this pattern. And again, you have this as a resource to help you when you're studying. I'd recommend going through the reactions by yourself, trying to make your own review sheet, and then check your review sheet with my review sheet. That's how I'd recommend it. Thank you all for coming to section. I know this is a lot. Let me know if you have questions. And we'll see y'all tomorrow in lecture. Thanks. Yeah. Also, if you do not put your name on the sheet, if you could put your name on the sheet. Also, where is the sheet? Cool. Thanks, Yam.
Probably forgot to.
Naya?
Yeah.
Okay, just before you leave.
I'm thinking like for the last.
Yeah.
So on this step, like very first thing we did.
Yeah.
I'm still like wondering why exactly like I understand that we find like coordinating our automated better. That was fine for me. I'm wondering how the addition of the forward
So we protonated the carbonyl, right? The carbonyl now has a positive charge on it. Oh, I thought you were talking about the other stuff. For this one,
Yeah. like,
Where-
Sigma and
because you went from a sigma CO to a sigma CO where there's positive charge. And positive charge lowers the energy of both the bonding and the antibond.
does. Is it that, yeah, okay.
So positive charge is actually like a proxy for like very electronegative. It says this thing wants a lot of electrons.
Oh, because we made it more electronegative, it's like holding on. Okay, that makes.
That's the rough.
What's that?
Anthony.
For these, is it any, oh wait, is that just to call them like?
It is, but it's slightly more involved because it is going to be the thing that supplies the hydrogen.
So that's what's giving, so the NADH four, is what gives this hydrogen.
Yes,
And then this
or
is-
no, it's what gives the hydrogen that's on the oxygen. Like, yes,
The NADH four is this.
yes.
Okay.
Yep.
Got it.
Yep. Hi, sorry for skipping you.
It's okay. Good question. So is the NADH4 what's providing this hydrogen? Is that what's going from? Or is
So
it
there are
both?
two hydrogens. So there's the hydrogen here. I'll do H1 and then the hydrogen here, H2. H1 came from this. Like this is your H1 from the sodium borehydride. Because that's the nucleophile attacking the carbon. The second hydrogen came from the MEOH. It came from there being a negative charge here and this grabbing the proton from MEOH.
Okay.
Yep.
And my question was,